Welcome everyone to this new episode of our Aerodynamics Analysis podcast. My name is Sergio, I'm here with my colleague Victor, and today we're going to analyze a very special guest flying wing. Site 3M has gave us their wing, their latest model, so we can have it analyzed for them for higher velocities that, as you may know, will consider compressibility effects. So Victor, if you want to introduce what our analysis consisted of.
Absolutely. First, we'll cover the methods we've used. After that, we'll go over the results. And finally, we'll go over all the conclusions that we draw from these. But first, let me mention quickly the assumption that we've taken. First, we're talking about a thin wing. Also, in the first analysis, we consider only incompressible regime. And as you can see here on the screen, these are all the design ratios that correspond to our actual flying wing. First, let's outline the objectives of our study. Our focus will lie on three main aspects. First, the relationship between the lift coefficient and the drag coefficient of the flying wing. Second, the aerodynamic efficiency. It is of extreme importance to know how the lift to drag ratio evolves and how it varies with the speed and angle of attack. And finally, we'd like to know the evolution of the angle of attack for steady level flight as a function of different speeds. First, we'll cover the experimental section of this study. We started analysis by testing a scale model of flying wing in an open wind tunnel. To simulate incompressible flow, we used a relatively low speed regime where the Mach number was pretty much zero. We're talking about a 10 meters per second constant airspeed. As you'll see now, however, it was far from constant. For the setup, we measured the wind speed using a hardwire anemometer, which is a device which translates voltage into airspeed. Then, the force was calculated with a balance that simply measured the difference in weight. However, this setup included many sources of error. Namely, we can mention the scale effects. Due to the reduced model size of our wind tunnel, the lower Reynolds number was introduced. Also, the wall interference cannot be neglected, since the tunnel winds introduce minor interference with the flow. Also, the flow instabilities are important, since there is no diffuser and the honeycomb was made out of flexible straws. Finally, it is important to mention the surface irregularities on the 3D printed model, since both the leading edge and the trailing edge were far from ideal geometrically, therefore inducing turbulence that cannot be neglected.
Now, we can move into the numerical side of our analysis for the incompressible regime. Here we used two different methods. First, we used a 3D panel method with the software XFLR5, and then we moved into MATLAB, where we developed our own code for a vortex lattice method analysis. So, first of all, 3D panel method. This method will model the wing as a collection of surface panels, where each panel will represent a portion of the potential flow around the wing. It will compute the induced velocity as well as the pressure distribution by solving the potential flow equations while enforcing the Cura condition that will ensure that the flow is smooth at the trailing edge. Unlike simpler methods, the 3D panel method will account for thickness of the airfoil, but in our case, it didn't really make a difference because the airfoil was already very thin. But this is important to mention it because, for other kind of airplanes, this will really make the difference. Now, on the other hand, the vortex lattice method will simplify the geometry further by modeling the wing as a series of bound vortices, which will be connected by their trailing vortices. This will calculate the lift by enforcing boundary conditions at the control point of each of the panels, and this control point was located at the center of each of those panels. While less detailed than the 3D panel method, the vortex lattice method did prove to be more efficient and also excellent for this kind of conceptual designs where you need a rapid estimation of what the aerodynamics of your airplane looks like. Now, both methods did assume certain assumptions like inviscid or incompressible flow, meaning that they will ignore viscous effects such as skin friction or flow separation. This will make them ideal to predict the lift in the linear region of the lift curve, but however, you will have also certain limitations. For example, in the vortex lattice method, it will be restricted to thin airfoils and will assume linear aerodynamics, so the nonlinear region, like that region near the stall, will be beyond of the scope. And then in the 3-panel method, it does not consider the wake rollup, assuming a flat wake, and in consequence, underestimating the induced drag. However, it will provide higher fidelity results than the vortex lattice method, but only in the case where thickness will really make a difference. In our case, as mentioned, thickness was not a big issue, and vortex lattice method did prove to be a better result in this case. In addition to numerical methods, we used another way to estimate the lift coefficient evolution, which is Prandtl's lifting line theory or Prandtl's lifting line formula. This formula will compute the 2D lift coefficient using the Cura-Joukowski to yield 3D results. So it is essentially an expanded 2D theory. But to calculate the 3D lift coefficient, we decided to account for sweep of the geometry, so we introduced a variation of the original equation, which was developed by Cushman, and this is called the Cushman formula. Here you may see the results by using this new formula, and Prandtl will assume a finite wing with elliptical lift distribution and also inviscid flow.
We'll now summarize quickly the incompressible flow results. First, all methods show a very similar CL versus alpha curves, confirming the reliability of potential flow models and lifting line theory for just preliminary incompressible design. Let me make that clear. Second, the experimental results cannot validate the CL results due to the low Reynolds number and the other sources of error introduced in the experimental setup. Finally, in order to continue this study into the compressible realm, we've decided to choose VLM, as Sergio mentioned already, due to its numerical simplicity when compared to 3D panel methods. We'll now take it to the next level and study the compressibility effects on this wing. For that, we've used a short-range turbojet with this wing geometry by studying its behavior across different Mach numbers. This will provide key design outputs, such as the maximum aerodynamic efficiency, the Mach number at which it is attained, and also the angle of attack for steady level uniform flight.
Before we transition to higher speeds, compressibility effects can no longer be neglected. And to correct this, we did use Prandtl-Glauer transformation method, which will modify the geometry to account for compressibility. Once the expanded geometry, as we like to call it, is obtained, you may use the incompressible formulas as if you were in compressible regime. So, how is this done? Not all dimensions are expanded in the same way, because while the y and the z-axis are expanded using the Prandtl-Glauer expansion factor, the x dimension or the x direction is not expanded. You can see that in the formulas from the screen. So, to illustrate how compressibility will affect our numerical models, here's the evolution of the wing mesh for an increasing Mach number. So, first of all, you will notice how at a Mach 0.5, the wing geometry will remain largely unchanged. But then, when we increase to a Mach of 0.7, the span-ways direction starts to contract, and this is highly noticeable for higher Mach numbers, as you can see for a Mach number of 0.9.
Let's briefly go over the logic that was used in order to get these results. As you can see here on the screen, the Prandtl-Glauer compressibility correction was only applied when the Mach number was larger than 0.2. After that, we used a very simple method in order to iterate VLM in order to get both the CL distribution and the steady level flight angle of attack. Now, let's see the CL versus alpha for different Mach numbers. It is extremely insightful, as you can see, that the CL alpha increases with the Mach number. So why is this? As the flow is compressed, there is a larger suction peak, therefore allowing for a higher CL. However, this effect is not entirely positive, since although this theory does not take account of it, in reality there is wave drag, so this cannot be increased indefinitely. There is a limit to it. So the increase in CL is somewhat counteracted by the penalty of wave drag. Now, let's go over the total drag plot. For lower speeds, it is mainly dominated by induced drag. However, at larger speeds, the parasitic drag takes over. It is important to note that an approximation has been done in order to estimate the parasitic drag, since CD0 is assumed not to depend on the Reynolds number. Let's test how good of an approximation this is. And to do that, we'll follow the flat plate model. For a Reynolds number twice as large, we have a CD0 increase of just 11%, therefore validating this approximation. Finally, let's discuss the aerodynamic efficiency, measured as lift-to-drag ratio. At low speeds, LD is limited by induced drag. Meanwhile, at high speeds, it is limited by parasitic drag. And right in the middle, the optimal point where LD is maximized, it occurs at Mach equals 0.63. This is consistent with the actual Embraer's E135 measurement, which states that its cruise is at Mach equals 0.78. However, this optimal point in reality is not so easily attained, since, as you can see here in this chart, achieving optimal aerodynamic performance would mean that you'll be having an angle of attack way too high in order for you not to stall.
To wrap this up, let us come back to some of the results that we were most interested in. First, the CL alpha increases noticeably as we increase the Mach number. However, it shall be noted that the level flight cannot be attained for Mach numbers lower than 0.5, because the angle of attack needed will be far too high, and as it is a linear increment, it is not physically possible. In consequence, the model does not consider stall nonlinearities and will yield unfeasible values. In reality, this is not an issue at all, because those lower Mach numbers will correspond to certain phases of the mission where the plane is neither steady nor leveled. For example, climb, descent, takeoff, or landing. Second, we shall study the drag as a function of velocity instead of the drag coefficient, for this can be misleading. It can be shown to be minimum at the Mach 0.63, as my colleague mentioned before. This result will have been much lower if the wing was not swept, because swept wings will attain their maximum aerodynamic efficiency at higher Mach numbers than rectangular ones. In our potential compressible theory, this can be explained with the fact that CL max will be reduced as the sweep increases. In reality, wave drag boundary also requires engineers to sweep their transonic wings. The taper ratio has also been optimized to increase the lift-to-drag ratio at a Mach near cruise conditions. So modifying the taper ratio will lead to lower aerodynamic efficiency and therefore a higher minimum drag.
Thank you, Sergio. A better model would include a CFD analysis, namely an LES or DES, large eddy simulator or detached eddy simulator. Solver with K omega turbulence model. This would therefore capture all the effects that have been neglected. For example, wave drag, turbulence, and other effects like trim drag and stall. Thank you very much.